Okay, I think we're live. Um, all right, so we finished. Wait, let me just do the toot toot. Yep, and then yeah. Okay, so we finished the intro to data science last stream. I took a break. Um, right now I'm gonna do this one course. It's called 6101. It's called Fundamentals of Programming, right? So yeah, it's called Fundamentals of Programming, and it's definitely harder than the the last course that I did, or significantly harder. So I'm doing the first lab for that, and for the first lab, I need to build an image processing system. So yeah, I mean that should be fun. So I'm gonna read the lab instructions and then try to code it up. So in this lab, you will build a few tools for manipulating digital images akin to those found in image manipulation toolkits like Photoshop and GIMP. Interestingly, many classic image filters implemented using the same ideas will develop over the course of the lab. For this week, we'll focus on grayscale images only. Okay, so only grayscale, but we'll revisit these ideas in the next week's lab. Um, let's see, digital image representation and color encoding. Before we can get to manipulating images, we first need a way to represent images in Python. While digital images can be represented in a myriad ways, the most common has endured the test of time. Rectangular mosaic of pixels, colored dots, which together make up the image. An image therefore can be defined by specifying a width, a height, and an array of pixels, each of which is a color value. Yep, the representation emerged from the early days of analog television and has survived many technology changes. While individual file formats employ different encodings, compression, and other tricks, the pixel array representation remains central to most digital images. For this lab, we'll simplify things a bit by focusing on grayscale images. Each pixel's brightness is encoded as a single integer in the range 0 to 255. One byte could contain 256 different values, 0 being the deepest black and 255 being the brightest white we can represent. Okay. The full range is shown below. For this lab, we'll represent an image using a Python dictionary with 4 keys. Um, Let me actually do. Yep. Okay. Using 4 keys. Mode either grayscale or color. For this lab, will always be grayscale. Okay. Width of the image in pixels. The height of the image in pixels, and pixels. A Python list of pixels in row major order. Okay, so listing from the top row left, so from here to here, and the next row, and so on. For example, consider this 3 by 2 images, 3 rows, 2 columns. Enlarge here for clarity. The image would be okay. The image would be encoded as the following instance: image mode grayscale, height 3, width 2 pixels. So 0. This is the darkest, right? 50, 50, 100, 100, and 255. Okay, so loading, saving, and displaying images. We have provided 3 helper functions in lab.py which may be helpful for debugging. Print values, load image, and save image. Each of these functions is explained by a docstring. You do not need to dig deeply into the actual code in these functions, but it is worth looking at those docstrings and trying to use the functions to load an image and save it under a different file name. You can then use an image viewer on your computer to open the new images to make sure what it was saved correctly. The print values function will work best on very small images. For example, test underscore images slash centered pixel dot png. Okay, so very small images. Okay, there are several examples in the test images directory inside the lab's code distribution, or you're welcome to use images of your own to test as well. As you implement the various filters described below, these functions can provide a way to visualize your output, which can help with debugging and also make it easy to show off your cool results to friends and family. Yep. Note that you should add code for loading, manipulating, and saving images under the under the main basically block in lab.py, which will be executed when you run lab.py directly, but not when it is imported by the test suite. Okay, as such, it's a good idea to get into the habit of writing code containing test cases of your own design within that block rather than the main body of lab.py. Okay, so I think this is the actual meat and bone of the lab. As our first task in manipulating images, we will look at an inversion filter which reflects pixels about the middle gray value. 0 black becomes 255 white, 1 becomes 254, and so on. For example, consider the following three images showing atoms, cats in each. The left side is original image while the right is an inverted inversion. Notice how in each example the darkest spots in the input becomes the brightest spots in the output and vice versa, while gray spots in the input result in similar but not necessarily identical gray spots in the output. Sure. Most of the implementation of the inversion filter has been completed for you. It is invoked by calling the function called inverted on an image, but some pieces have not been implemented correctly. Your task in this part of this lab is to fix the implementation of the inversion filter by finding and fixing errors in get pixel, set pixel, and inverted function so that the work is described. Before you do that, however, let's add a small test case to test.py. We'll start by figuring out by hand what output should we expect in response to a given input and writing a corresponding test case. Let's start with a 1x4 image that is defined with the following parameters. Grayscale, height 1, width 4 pixels, 22, 88, 136, and 197. Through an inversion filter, what would the expected output be? Compute the result in hand, then in the box we'll enter a Python list represented the expected value associated with the pixels key in the images. Okay, fair enough. Let me just open Canva. Cool. I have Canva opened up. Let's see. So it's 22 is gonna be 256 minus 22, 255 minus 22. So all of this is just gonna get subtracted from 255 for the inversion, right? So let me bring up the calculator because I want to do it fast. I'm just gonna use my phone. Calculator. 55 minus 22, that's 233. So that's the first one. 55 minus 88, that's 167. 255 minus 136, that's 119. And then it's 197, that's 58. So that is gonna be the list, right, that we're gonna get. Let me try and verify my result. Okay, so that works. Okay, adding a test case. While we could just add code using print statements to check the things that are working, we'll also use this as an opportunity to familiarize ourselves a bit with the testing framework we're using in 611. That's PyTest. Let's try adding the test case to the lab's regular test so that it is run when we run test.py. If you open test.py in a text editor, you will see that in a Python file that makes use the Python package PyTest for unit testing. Yep. Each function has a name starting with test in test.py represents a particular test case. Running test.py through PyTest will cause Python to run and report all of the tests in a file. However, you can make Python run only a subset of the tests we're running. For example, the following command from a terminal, not including a $sign. So only the load, right? This will run any test with load in its name. In this case, the load test defined is the test load function. If you run this command, you should get a brief report indicating that the load test case passed. But by modifying the last argument load in the example above, you can run different subset of tests. Okay, you can add a test by adding a new function to the test.py file. Importantly, for it to be recognized as a test case, it must begin with the word test. Okay, in the skeleton you are given, there's a trivial test case called test underscore inverted 2. Modify this function so that it implements the test from the above, inverting the small 1x4 image. Within that test case, you can define the expected result of an instance as an instance of the hard-coded dictionary. You can compare it against the result from calling the inverted function on the original image. To compare the two images, you may use our compare images function. You can look at some of the other test cases to get a sense of how to use it. Your test case should also check to make sure the input image was not modified. Once you've implemented your function, paste it into the box below. You do not need to include the other function / code from test.py. When you submit your when you submit the box below, we will check your test case and several implementation of inverted, some of which work and some of which don't. Now that you've tested this function, copy it back into your test.py, replacing the existing test underscore inverted so that it runs every time we run test.py. Even once we've implemented this function, we should also expect the test cases to fail when run on your own code. After all, we haven't finished fixing the inverted filter yet, but we can expect it to pass once all the bugs in the inversion filter has been fixed. In this way, it can serve as a useful means of guiding our bug finding process, i.e. as long as it isn't passing, there are still more bugs to find. Throughout the lab, you're welcome, and you may find it useful to add your own test cases for other parts of the code as you're debugging, and any extension or utility functions you write. Any function that starts with the word test will be interpreted by PyTest as a test case. Okay, I think this can't be that hard. Let me get to the code. Okay, so we need to do a test case. There's compare images. Okay, test load, test inverted 2. That's what we're gonna. Right, so let me look at test inverted 1. So this is input file name, input image, result image. Okay, expected image is this one, and then through object underscore hash we're doing be careful not to modify the original image. Okay, so let's look into it. So we need to do for our input image, right? It's gonna be let's do this, input underscore image. It's gonna be a dictionary, so the mode is gonna point to grayscale, right? Nope, not capitalize. The height is gonna be that of 1 the width, that's gonna be 4, and pixels, that's gonna be 22, 88, 136, and 197. Okay, so that's the input image. Okay, now the result image is gonna be lab dot inverted. Yep, the input image. And now the expected image. Expected image is gonna be mode grayscale, because it's gonna be a grayscale image, right? The height is gonna be 1, it's not gonna change. Width is 4, and then pixels is gonna be the answer, which was 233, 167, 119, and 58, right? And comma here as well. Okay, we okay, okay, so we have the pixels. Now what we can do is compare images, right? Result, yep, result image with our expected image. And then we can do okay, we can do assert object hash, so that function, and then we can do input image equals okay, so there's input hash. What is that? So this is the input image, which is the input image, and then for input hash, is the object underscore hash? Okay, I have no idea what this does. This probably does some um like bit level manipulation that I just don't know. I just don't understand. I'm just gonna follow whatever was done here. Input underscore hash equals object underscore hash, right? Input image, and then basically do whatever equals input hash, yeah, be careful not to modify the original image. Okay, this should be correct. Let me check. Okay, so it says my code is good, you know. So I think we can move on, right? Okay, now work. Let me just. Okay. Oops. Okay, now work through the process of finding and fixing the errors in the code for the inversion filter. The bugs that you fix will be discussed as part of your checkoff, so it's a good idea to add comments and describing all of the bugs you found and fixed as you're working, as you'll be expected to talk about not only your fixed code but also the nature of the bugs you found in the original code. Happy debugging. When you're done and your code passes all the inverted test case, run your inversion filter on the bluegill.png image, save the result as a png image and upload it below. It's a green check mark. If not, you'll see X. It is also good to go ahead and submit your code to the server. Remember to submit early and often. Okay. Sure thing. Okay, so fixing the code. Inverted. Where is inverted? There we go. Okay. Get an image. Produce a new image that has all. Okay, so process should not mutate the original image but rather should create and return a new image. So I think we're doing that. We have result mode, grayscale is good. Height is image height, width is image width pixels. Okay, so we're iterating over the width and then the height. Is that correct though? And I can already see that this is gonna be 255, not 256. So there's that. I always get confused over the width and the height thing, like always. The question is, does it matter though? Because I know it's a 2D image, but we're not really storing it as a 2D. I mean, I suppose for the row and the column, it does make sense. It does make sense. So 3 is the rows, right? So that's gonna be first row, second row, third row, and for the columns it's gonna be like this. So that's height, right? When we do the columns, so it's gonna go like this, and then the rows is gonna be like this. So okay, we do get pixel, so we get the pixel from that row comma column, right? um yeah, image row column, and then we do set pixel. Okay, and then we return the result. This should pass. I feel like the only bug was 255 here. I'm gonna just open my terminal. um Let me do something here.
Suddenly, this number is changing.
Oops.
Okay.
Shared basically everything. That's not what I wanted. Properties. Properties. Application capture. Terminal. Okay. So let me do the PyTest thing. So it's gonna be PyTest test.py inverted, right? So inverted v. So I have a lot of errors. Okay, so these are all the errors that I have. List indices must be integers or slices, not tuple. So it's the type error. List indices must be what? Interesting. So that is happening on get pixel, right? Yeah. So if I have VS Code, so that is happening on get pixels. So what is it doing? This, if we do image, wait, that's just gonna be what is that gonna be? That's just gonna be an integer, right? Which is gonna be something like 0 to something. So I'm just gonna do yeah. So if we look at our test case that we have, so our input image is 1 4, right? Okay, so if it's 1 4, it's gonna be 4 and then 1, so 4 1, so this is gonna be 0 at first and this is gonna be 0. So and then it goes to get pixels column comma row. Am I supposed to debug get pixel and set pixel as well? Because this seems wrong to me. Let me just read the problem set again. Okay, so I need to fix get pixel and set pixel as well. So it's doing row, column, right? So it's gonna be row and then call, and this is also gonna be row, call, right? This should fix things up. Okay. I get that, because yeah, that doesn't make it right. It doesn't make any sense. Yeah, so it's gonna be times column, right? If we think about it, or row plus column. Let's see. So if we have 1/4, so it should be row plus column, right? Not row times column. Okay, hopefully my intuition is correct. Key error width. That is insane. That shouldn't. Oh, okay, buddy. Oh my god. There was a typo. Key error width. Okay, let's see now. That is crazy. That shouldn't have a key error. I shall be back. Okay. Um, I had my lunch. I'm filled up. Now let's try to knock this image processing thing out, right? Let me open the camera. There we go. Okay. I'm going to make this bigger. No, not like this. Oh. Okay, so the problem is it says key error with which I mean one of the reasons could be that I don't have pillow. So what if I do pip install pillow? Oh, I think it's homebrew, right? For Mac. Yeah, I think it's homebrew for Mac. But I don't think it's because of pillow that we're getting this error. It says, or maybe it could. No, it's not because of pillow, or maybe it could be. I don't know. Doesn't hurt trying, right? I install pillow on my Mac. Maybe we need to do pip3 install. It says externally managed, so that's the whole homebrew thing, right? I'm just gonna paste that to Claude. So it says to do like a virtual environment. Sure, I mean, okay, yeah. Okay, let's run the code to. It's still which pip. Yep, so pip is here. It's still getting a key error of width, so that's happening in lab.inverted. Where okay, width set pixels. This is wrong. Lab.by image equals height 11 mode race. So what? correlate. Where's the inverted? So when I'm doing set pixels, 255 minus color, it's going to set pixels, it's doing height 11, mode grayscale. And here it's doing, so one thing that I can do is HD. So HD, nothing here. I can do the same for this. What? HD. Okay, nothing here as well. So where are we getting the wrong spelling from? That's crazy. Clearly we're getting the wrong spelling somewhere. This is the problem, right? This is width, this is width. Width, WID. Let's go from the top. Okay, width. Yeah, if we do that, there's no results. If we do width, I'm pretty sure there's like, for some reason it's finding this. So first it's doing, okay, so it's doing inverted 1, right, and it's doing lab.inverted input image, and then so this is test images centered pixel, and then in here it's going to, so it's calling my function of inverted, and in inverted, it's the image is height, mode grayscale, pixels, and with, so this itself is creating the input image itself has width as WIDHT. That's not what we want. And our task is to fix the implementation of the inversion flow by finding and fixing errors in get pixel, set pixel, and inverted function. So because this is what it means, right? So in here for some reason it's width, so this is calling input image is load image, and for load image, I don't know where, no, I'm wrong. Oh, okay, I probably didn't just save it. Yeah, okay, so list assignment index out, this is an error that I expected to happen, or like the row plus column. Okay, so that's sure, I guess. So row plus column is causing out index out of range. let's try to use it for our example, right? Let's try to, I'm gonna run the code, but for my example. So if we do Safari, there we go. Okay, so we had 22, right? 88, 136, 88, 136, and then 197. 197, right? We have height 1, so h is 1, and then width is 4. So it should be if I'm not wrong, height here and then width here, right? So the way it's gonna work is, and this is for only this test case, right? But so it's gonna go up to but not including 1. So it's only gonna execute 1 time. Okay, and then this is gonna go from 0, 1, 2, 3. So this test case should pass. So it's gonna be 0 plus 1, 0 plus 2, 0 plus at first it's gonna be 0 plus 0, 0 plus 1, 0 plus 2, and 0 plus 3. So it hits all of these, right? Yeah, that should work. Let me run the test case. Okay, even for inverted 2, that's crazy. Oh, yeah, so I think if we do 0 times, yeah, row times column. Yeah, we can just do image height times image width. There we go. Clear this. Okay. Okay, so we're correct. It's just the pixels aren't matching right now. Let's look at our test case. So we're getting 0, 0, 58. While in reality we're supposed to get, so we got the we're only getting the last result to be true. Yes, so there we go. Okay, so the first one works. Well, our specific test cases work. These don't. So let's see. Okay. So the expected was gonna be um all 255 and then 0 here, right? Hmm. Ay, ay, ay. Okay. Not mushroom. Let's just do this one. So I'm thinking if we have 0, well, we're only gonna subtract by 255, so we don't need to do mod. We just need to get the absolute value. So absolute value. Yeah, so okay, I mean, this shouldn't make that big of a difference, right? Well, we don't even need to get the absolute value because this value is gonna be not greater than 255, so there's that. So the ABS function literally does nothing there. Okay, so at index 21, so at row 1 column 10, so at row 1 column 10, my actual thing is just gonna compute to 11, but that is index 21. So why would that be? Let's see. So it's 11 by 11, right? So if it's 11 by 11, at first it's gonna be 0, and then it's gonna keep going to 11. Then it's gonna be 1, and this is gonna turn to 0. But we want this to keep incrementing, right? So we have to flatten, or I mean, we can make the pixels to be a 2D list, but I don't think so that's what they want, because this is a 3 by 2 image and this is still 1D, right? So we need to do some indexing arithmetic here. It's not going to be multiplication, and it's not going to be addition as well. Because it's more going to be like the count, so the overall count. Okay, are we allowed to change, like add one more parameter? I would have just inverted. I would have just added the parameter count, right? And then that basically so if we have the parameter count on set pixel and get pixel, we can use that. gist of the whole row plus column thing, because I'm wondering if I can somehow get it based on the row plus column thing. I mean, we can do this. So once both row and column. I was gonna say we can do like for I in range row times column, right? And then call it with I. So I'm trying to think. Is there a way where we can have the row, so if it's a 2 by 2, then this is gonna be something like this: 0 1 2 3. You want to access the last element, so that's gonna be 4 minus 1, 0 1 2 3, right? So it's gonna be the third element. If you want to access the first element, then my row and column is gonna be actually this is gonna be 1 times 1, so 2, right? So we had 1, that's 3. So, but if you want to access the first element, it's gonna be 0 times 0, which is 0. If we, that's the first element, that's all right. And the second element is gonna be 0 times 1. If you take the max, okay, and then we have 1 times 1, which we can't take the max, it's just gonna be multiplication. That's gonna be, that's gonna be 1 times 0 actually. 1 times 0, if we take the max, okay, and that's gonna be 1 times 1. For that we can do 1 plus 1. I mean, is that universal though for my calculation? So something like, if row times column equals 0, take the max of row and column. Otherwise, do row times column plus 1. But let's see if this is true in all cases. Let's just do let's see a couple of examples, right? Okay, let's just do 3 by 2. So we have this. Okay, so it's a 3 by 2 image, so 1 2 3, 1 2 3. So this is like the image, right? 3 rows, 2 columns, right? So Okay, so 3 by 2, right? Okay, so at first it's gonna be 0 0. Take the max of 0 and 0, so 0, we have that. Okay, then it's gonna be 0 times 1, take the max, which is 1, so 3 by 2, so we have 50, and then we 1 times 0, so yeah, take the max, but the max here is 1, we can't take the max. I could change the row comma column. Is there a calculation of getting the index through row comma column? Okay, so it's something called row major order. Okay, so it's row times total column plus column. Okay, interesting. So it's something called row times total column plus the column that I'm looking right now. Let's see how this works out. So my total column here is 3, so 0 times 3 is 0 0. Okay, so I'm still in the first column technically, right? This is the second column, this is the first column, or maybe my understanding of row and column is very different. Column, yeah, so these are row, yeah, so that is rows and that is columns. Yeah, so I see. So when I do this, I change the column, still on the same row. So inverted so this is fine, we just need to do the whole thing of the calculation, right? So it's gonna be row times total column, which is gonna be my width, right? Yeah, image width plus the current column. You mean code is structurally unreachable? Call width plus call. Yeah, so that's what I'm doing, right? So So I'm gonna do row times image width, right? I'm gonna put that in a bracket plus the column that's equal to the color. Now this should pass all the test cases. There we go. So that was the calculation, right? So it's row times whatever column I'm at plus the total column. Okay, let's move on. Image filtering via correlation. Now we'll explore some slightly more advanced image processing techniques involving an operation called correlation. Before you start writing code, we encourage you to read all of this section, answer the small concept questions, and make a plan of how you will implement this behavior. Okay. Given an input image I and a kernel k, applying k to I yields a new image O, perhaps with a non-integer pixels outside of the range 0 to 255, equal in height and width to I, the pixels of which are calculated according to the rules described by k. Okay, the process of applying a kernel k to an image I is performed by as a correlation. The brightness of the pixel position r, c in the output image, which will denote as ORC, okay, is expressed as a linear combination of the brightness of the pixels around positions r, c in the input image, where the weights are given by the kernel k. Okay, as an example, let's start by considering a 3x3 kernel. Okay, so 0 is gonna get multiplied to the first, 1 to the second, 0 to the third, so on, right? For the remainder of this slide, we're going to represent a kernel as a dictionary mapping r, c coordinates of the values associated with 0, 0, representing the center value of the kernel. We will assume that both dimensions of our kernels are odd in length, so that there is always an unambiguous center value, and only including non-zero values. So the kernel above, for example, will be represented as -1, 0 pointing to 1. Okay, so -1, 0. So this is 0, 0, then -1, 0 is 1. This kernel to an image, the brightness of each output pixel is a linear combination of the brightness of the 9 pixels nearest to r, c in I, where each input pixel is multiplied with the associated value in the kernel. In general, for a 3x3 kernel, we have this lab is hard, right? Blurring. Okay, it's not that big though. Okay, so for our output, right, okay, so for our input r -1, c -1, so 0, 0 is the center, right? So r, c, 0, 0 is the center. That's where the value is gonna be at. So that's gonna be okay. Multiplied by this, plus, okay, so we're doing all the addition and multiplication, right? And then whatever value we get, we put it in the center. For example, applying the kernel k above at the center pixel in row 2, column 2 in the 5x5 image, which contains arbitrary pixel value, because, okay, so it says 42 gets placed here. Well, does it though? Row 2, column 2, so 0 1 2 2, so it's this one, right? Okay, so this is a 3 by 3 and this is a 5 by 5 image. For okay, so we're gonna do, so we take a 3 by 3 part, okay, and then what we do is we're doing 40 times, okay, 40, and then we, okay, and then we whatever value we get, we put it here. For kernels larger or smaller than 3 by 3, we follow a similar pattern, always with input r, c aligned with k00 at the center of the process. Consider one step of correlating the image with a following 3 by 3 kernel. So it's 0 0.0, negative 0 0.07, 0 0.00, and then negative 0.45, 1 point. Okay, that's a 3 by 3 kernel, which would be represented by the following dictionary. Okay, so negative, so this is 0.07, 0 minus 1, so that is this part, yeah, point minus 0.45, that's 1.20, that's negative 0.25, that's, yeah, okay. Given an 3 by 3 image with the values below, what would be the value of the center pixel output image? Enter a single number in the box below. Note that although our input brightness were all integers, this value will be a decimal number, of course, because we're multiplying it by decimal numbers. Let's see. Okay, so we have this as a kernel, 0.00, negative 0.07, 0 0.00, negative 0.45, and then 1.2, negative 0.25, 0 0.00, negative 0.12, and then 0 0.00. Okay, so this is our kernel, and then this is our 3 by 3 image. So we have 80, 53, 99, 129. Whoops, what happened? Okay. So we have 129, 127, 148, and then 175, 174, 193. Okay, cool. So there's this one. Okay, so we're gonna do significant calculations here. So it's gonna be 80 times 0 plus 53 times negative 0.07 plus 99 times 0 plus 129 times negative 0.45 plus 127 times 1.20 plus 148 times negative 0.25 plus 174 times negative 0.12. My handwriting so bad. negative 0.12 plus 193. Well, I don't need to do anything to that. It's gonna be 32.76. So is that correct? Let's see. Let's verify. Yep, apparently it's correct. Okay. Okay, HFX. Before we continue with actually implementing the correlation operator, there is one additional wrinkle we need to consider, which is that correlation requires accessing pixels that are outside of the bounds of the original image. Yeah. For a specific example, consider the top left pixel 0, 0. All of the pixels to the top and the left of 0, 0 are out of bound, but they should still factor into correlation. Currently, though, accessing pixels outside of images causes things to break, so we'll need to adjust. There's a bunch of different ways we could handle these out of bounds, but for now, we're gonna handle things in a very specific way. We're gonna modify get pixel so that it accepts out of bound location, but always returns 0 for those pixel values. In effect, we're gonna treat the image as being infinitely large, surrounded on all sides by 0 values. Let's just do that, right? Okay. So everything was gonna be so. Let's see. If row size is gonna be row times column, right? So it's gonna be row plus image width, right, plus column. So if it's less than 0, or row plus image row plus image width, width plus column if it's greater than size, then return 0. Yep, that should work. Okay, now correlation. So the remainder of this lab we will implement a few different filters, each of which involves computing at least one correlation. As such, we will want to have a nice way to compute correlations in a general sense. Okay, for an arbitrary image and an arbitrary kernel, Note though that the output of a correlation need not be a legal 611 image. Pixels will be outside the 0 to 55 range or maybe float. Since we want our filters to output valid image after the correlation process is finished, each filter will need to clip negative pixels to 0 and values greater than 255 to 255, and to ensure that all values are in the image are integers. Because correlation and making an image have valid pixels are common approach, you can implement them separately rather than a single function that performs both operations. We have provided skeletons for these two helper functions, which we've called correlate and round clip image respectively. Okay. For now, read through the doc strings associated with these functions. We'll come back to implementing them in a bit after talking through some of the important pieces. Okay, let's see. So it says create and return a new dictionary representing the result of correlating the given image with the given kernel. Okay, the process should not mutate the image. It should output a new image dictionary where the pixel values would have not been rounded or clipped. Okay, and then round and clip is create and return a new grayscale image representing the result. Okay, so fair enough, simple enough, right? Well, round and clip should be pretty simple. Correlate can't be that hard, right? Okay, example kernels. Many different interesting operations can be expressed as correlations, and many scientific programs use this pattern, so feel free to experiment. Identity. The above kernel represents an identity transformation. Applying to an image yields the input image unchanged. Okay. Translation. The above kernel shifts the input image 2 pixels to the right, discards the rightmost 2 columns of pixels, so this one and this one, and replace the 2 leftmost columns with zeros. So okay, so it discards the rightmost 2 columns of pixels. It will discard these 2 and then replace the 2 leftmost columns with zeros. The each pixel is the average of the 5 nearest pixels of the input. Given the 3x3 kernel K and the grayscale image with 3 rows and 2 columns below, if you were to correlate image I with kernel K, assuming the value out of bound image are all 0, what would the expected output be? Compute this result by hand, then in the box will enter a Python list. Okay, fair enough. You may also want to write a few test cases comprised of correlating 11 by 11 or the simple image with a few different kernels. You can use the kernels in the previous section to help test your code produce expected results. Now that we have a sense of reasonable structure, it's time to implement correlate. So we can so the plan that we can do is before that I want to do something interesting. So we did our inverted thing. We haven't really tested it out. I look, you want to see when we tested it out, but we haven't tested it out with an image, and that's the fun part, right? Testing it out with an image. So let's just do that. So test images. This is okay, this is a blue fill. If we test it out with yeah, so let's do load image. Instead of cat.png, it's gonna be bluegill.png, right? Bluegill.png, and then equals to inverted x, right? And then is there anything called show image or save image? There is print values, load image, there is save image. Okay. So save image y comma inverted bluegill. I think I want to do, is this already going to output images? I think so. I think it's already going to the output images, so we can do bluegill underscore inverted dot png, and then we can run our code. Python 3 lab.py. Okay, cool. I do not know where it was saved. .8 or newer. Okay, I need to upgrade my this is still bluegill. Where was it saved? That's interesting. It ran perfectly fine, I suppose. It says invalid syntax. Which Python? Python, to check Python version. Okay, so Python version. Okay, so this is the latest version. There we go. Okay. Bluegill invert. Yep. That's what we expected. So this is the original image. This is our inverted image. Pretty cool, actually. I think when we do the colored version, it's gonna be even more cooler. But yeah. Okay, so the plan, right? The plan was to okay, so we need to do this calculation of the whole image, and then we can write a few test cases. We can do the test cases for the 11 by 11 centered pixel, right? And we can do it for the 3 by 3 kernel, this one, and then the translation kernel, right? We can do that. Or we can honestly just use this, because we're already computing it, right? So we already know what the answer is going to be. So we can use that as a test case, and then we can use that with, can we use it with the 5 by 5 kernel? think we can, right? We just have to um for there's gonna be a lot of zeros, right? So for each values there's gonna be like, so if we do 2, it's 5 by 5 kernel, then we're gonna, not only are we gonna take the whole thing, we're also gonna pad it all the way there. And then we can implement correlate, and then keep and then run it on whatever. Okay, so this is gonna be, and then it's gonna be blurring and sharpening. Okay. Two. Okay, let's calculate this thing. Okay, so the kernel is, oh my god, nope, not this one. The kernel is 0, so it's all zeros except the last one. Okay, so 0 0 0 0 1. There's a 3 by 3 kernel, and then we have 3 rows and 2 columns, so 20, 40, 60, 80, 100, 120. Okay, 60, 80, 100, 120. Okay, so if we do, if this is, okay, so this is gonna be 0, 0, right? So we're gonna do, the image is gonna be 20 is gonna be in the center, 40 is gonna be here, 60 is gonna be here, 80 is gonna be here, right? And then in here it's gonna be 0 0 0 0 0. Let's see what I did technically. I'm thinking about it like code. So we're gonna get the pixel, and then since it's a 3 by 3, we're gonna run it, since it's a 3 by 3 kernel, right? And this is 20, so we're gonna have to run it 3 times basically. So 3 times 3 times, right? And it's gonna be this is gonna be a bitch to code technically. So this is gonna change to 40. One other question. Well, we are still gonna iterate over the original image, so this is still gonna be 20, and then when we're creating a new image, so 40 here, and then same thing, but it's gonna be 40 is gonna be the center thing. This is gonna be 0, and then this is gonna be 20, correct? The upper row is fine, and for the row below, this is gonna be 80, this is gonna be 60, right? And then this is gonna be 0. Oh no, I definitely made a mistake, didn't I? Because, yeah, if we do 20, right? So 20 is going to be our center pixel. Okay, and let's try to do it in code. How would we do it in code? So this is a 3x3 kernel, right? And this is 0. So iterate to the right. How many times do we want to iterate to the right? We don't want to do that 2 times, because if this is the center, then we're gonna do the difference. So what values are we gonna have? We're gonna have 3 and 3, right? Kernel is gonna be a dictionary wrapping row comma column. So we have a 20. So for the kernel, it's gonna be the center of the kernel, right? So it's gonna be a dictionary. It's gonna have -1 comma -1. So, right? So whatever row column value that we have here, which is gonna be 0 comma 0, we can subtract that, and that should give us the value. Okay, so that's how we can do it code wise, so at least we have the algorithm figured out. Okay, so it's gonna be, let's see, and then for then it's gonna be after -1 -1, so it's gonna be minus, so so for -1 -1, so 0 here, and then it's gonna be -1 0, which is also gonna be 0, and then it's gonna be -1 1, which is also gonna be 0, right? And then it's gonna be 0, -1, which is also gonna be 0, and then it's gonna be 0, 0, which in this case is gonna be 20, right? And then it's gonna be 0, 1, which is gonna be 40, and then it's gonna be 1, 0, which is gonna be actually no, it's gonna be this is 0, 1, so 0, 1. That's gonna be so this is 0, 1, 2. So this is 0, 0, so this is 0, 1. This is gonna be 1, -1, so that's gonna be a 0, and then it's gonna be 1, 0, which is gonna be 60, and it's gonna be 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So that is gonna be 80, right? Despite saying all that, the middle value is just gonna be 40. Okay, now we move on to 1, 0 as our pivot point. So 1, 0, so 40. Okay, so with 40, right, let me just erase this. Okay, so with 40, what are we gonna have? So again, it's gonna be -1, -1, so it's gonna be 0, -1. So that's 0, and then it's gonna be 0, 0, which is 20. Cool. And then it's gonna be 0, 1, which is 40 in this case, but we don't want that. So you see the problem. Well, I think we're doing a mistake. So if we consider 40 as 0, 0 now, I'm just trying to think. I mean, I can do the calculation right now. That's not gonna be too hard, but I'm just trying to think how to do it in code. So have some algorithm in my head that I can just implement, right? So if we do in code, it's just gonna be 20, 60, 80, right? 0, 0, and then 0, 0, 0, right? So in the end, this is just gonna turn out to be 0. How did we do that in code though? That's the main thing that I want to figure out, right? Because at this point 40 is going to be my center pixel, so 40 is going to be 0 0. So by our logic we're doing -1 comma -1, right? So if we did -1 comma -1 to 0 comma 1, this is 40, right? So at first we were gonna get -1 0, and then we were gonna get, oh, I think I did a mistake in my calculation, and then we were gonna get -1 1. Okay, so that part is done. Okay, and then with 0 comma 1 we were gonna get if we're here, right, we should get 20, and this part is gonna be 0 -1, so we get 0 0, which is 20. That is correct. And then 0 0 here is just gonna give us 40, and then 0 1 is just gonna give us 0 1 is just gonna give us 0 plus 2, but that is gonna get out of bounds, so we're gonna get 0. Okay, I think I get the algorithm right now. I'm just gonna speed through the rest of them. Okay, so we have 40 0 and then comma so 60. So for 60 we get, this is the center pixel, we are gonna have an 80 here, a 0 here, a 20 here, a 40 here, a 0 here, 100 here, a 120 here, and a 0 here. So that is gonna give us 80. Okay, 40 0 80, and then what else? 40 0 80, and then for 80 we're gonna get a 0, because this is centered, then to its right there's nothing. For 100 we are gonna get 120, so it's gonna be 40 0 80 0 120 0. So let me see if the answer is correct. Yeah, so the answer is 40 0 80 0 120 0. Okay, so now go to debugging. You may want to write a few test cases comprised of the 11 another simple image with few different kernels of different sizes. You can use these kernels the previous shell that produces test your code produces the expected results. Okay, so the way I'm gonna do with this test cases is I'm gonna write the correlate function, right? And if I get stuck on something, I'm gonna use these test cases to write to go through my code. I'm gonna write those in the main function, so that way I can actually see any output values that I do. So I think I can just write my correlate function. So that's the function that we want to write, right? Or are we supposed to do so we will do correlate and then the round and clip, right? So let's do correlate at first. Actually, let's do round and clip at first. That makes more sense. So it says create a new grayscale image dictionary representing the result of transforming the pixel in the given range into integers with the valid range 0 to 255. So how does that work again? So this is easy, so we don't have to do any mod thing here, right? So if any pixel is, so we can do so let's see, result equals to yeah, so we're gonna do mode, it's always gonna be grayscale, right? Not capitalize. Yep, and then height is always gonna be my image height, and then my width is gonna be my image width, and then for pixels, right, we're just gonna do this. So pixels, yeah, we're gonna have the list, right? And then we can just do this. For I in range image height times image width, this is gonna be 0 times just copy this, yeah, and then get rid of the extra thing. Okay, so image height times image width. Okay, so if image pixels, right, and then inside pixels I, if it's greater than 255, then we'll do result pixels I equals to 55. L if image, right, pixels I, if it's less than 0, we're gonna do result pixels I, we're gonna set that to 0, otherwise we're gonna do equal to whatever the value of image was. And then we can return our result. Okay, this should run all the test cases in test.py. Let me just check. Okay, so is there test cases with I'm gonna do pytest test.py actually. Pytest test.py and then see. Yeah, exactly. So our get pixels what? Or inverted should be okay. Doesn't make sense for inverted to be ruined because we didn't change anything there. In no way. Or inverted was working. Okay, so we don't have we have correlate. We don't have anything for round and clip, which is fine. I mean, but why is our inverted not working anymore? What the? What did we do? I mean, it was working like a few moments ago. Then I changed this for get pixels, so this is the only thing that makes the most sense. Yeah, so it's gonna be row times and then row times, and that should. Okay, so that didn't fix anything. That is crazy. That is crazy. I thought that was gonna fix like a lot of things. It didn't fix anything. Okay. Um, Insertion error. Pixels must match. I mean, sure, but it was working. Like that's. I'm not deluded when I say it was working. So what's happening all of a sudden? It's just these lines of code. That's all I added, right? So if I get rid of these, yeah, it works. So it's this lines of code. These lines of code are breaking it. But what is wrong with these lines of code? That's the thing. That's what I'm trying to find out. So saying if it's out of bounds, right? Okay, so it's still broken. Hmm. Oh my god. I think the best way we can do it is test it out. I mean, that's the best thing we can do. It also fails in. It fails in test underscore inverted too, which. So expected was 233 119, we got 233 167, and then we all got 255 for the rest of the values. So which means it's returning 0 and we're doing 255 minus 0, right? So let's try to see why that's happening. Okay, so okay, this way we can see all of it. Okay, so we have 22, 88, 136 and 197, right? Okay, so our column is 0, our row is 0, we call get pixel. The first one is fine, it's 233. I mean, that's fine. Okay, the next one is our row is 0, our column is 1, which is true. Our column is in this case 1. We're going from here to here. Okay, so our column is 1. So this is height is 1, width is 4, so row is 1, r equals 1, c equals 4, right? So what are we doing here? We're doing row, which is in this case 0. So we're doing 0 times our total width, which is 4, which is 0, plus 1, right? Because column at this point is 1. So is 1 less than 0? It's not. Is 1 greater than the size that we have, which should be 4? It really isn't. So we're not supposed to return 0, we're supposed to return I am just gonna save it and guessing just, and then maybe run it again and hopefully yeah, I mean that wasn't it. It's the debugging, man. Yeah, so it's clearly returning 0 for all the rest of the image, which I don't understand. Because if row times image width is 4, row is 0, so 0 times 4 plus 1, maybe it's a issue of brackets, man. Maybe all I need is just to add a bracket here, add a bracket here, add a bracket here, compute this whole thing. Okay, never mind. Can't be that easy now, can it? How many do we fail? We fail 1, 2, okay, so we fail a lot. Chess, yeah, 2 cats, mushroom, yeah, it's the same error. Oh. Why would there be an error like this happening here? I suppose we can, I mean now is the best time, right? Do print, because that's how I debug. I just have like a shit ton of print statements. So if I copy the code, what do I even print though? That's the other thing. I suppose row comma column can help. If we do print row comma column, and then I think if I do inverted, right, underscore 2, so specifically the second one. Nope. It should run the 1. Does it execute the? It does execute the print statements. Okay. So yeah, 0, 0, 0, 1, 0, 2, 0, 3, just how we expected it to be, right? So I see my problem. It's not gonna be okay, my bad. It's gonna be image height times image width, and not only that, I ought to subtract 1 from it. Yeah. Now I feel like all of it should work. Okay, cool. Desktop by Okay, so get underscore pixel has one small error. Um, so let's fix that. It's oop get underscore pixel. Ooby get underscore pixel. Okay. Let's see. So expected is this. So my height was my row was, what was it? Oh, what's happening here? Height is 220, width is 300. Insertion error. Yeah, just put this in the front. Still an insertion error. Okay. Oh. That's crazy. Let me look at the code. So what is happening in here? So at first this is the expected. It gets paused in this one. So R comma C, right? Okay, so my image height basically throws in assertion error. I wasn't supposed to get any assertion error. I was supposed to get the pixels. Is there any change that we do to get underscore pixels later on? Let's see. So no more changes. That's the only thing that we do because it doesn't get mentioned anymore. And then So when we do this, or like, I think I understand. So row, so this is doing what? Row -1, column 146, and this is doing row 220, column -9. It wants a 0 for these, right? So it's a 220 by 220 image. So 220 by 220, right? And it's doing row 220. So my row is 220, my column is -9. So I think I have an easier way to do this. Can I do assert else? Python. Yeah, so not return 0. And then we don't need the assertion here. This way. And now if we do pytest test.py, yep, okay, we are getting there. Okay, so now we should be able to start on correlate. Hopefully my round and clip is correct. So I think this is correct. Let me check though. Right, so okay, so I did the rounding thing correct. I just didn't do the clipping thing. So that is not that hard, right? Or we can do round image pixels. Okay, that should be okay, right? So that works. So that is correct. Now the what else do we have left? Yeah, the correlate thing. This is gonna be interesting to write. Okay, so we have image and we have kernel. So create and return a new dictionary representing the result of correlating the image with the given kernel. Should be fun. Okay, so result, I'm just gonna copy this. Okay, now the actual logic, right? So let's see, a kernel is a dictionary mapping r comma c to indicate kernel values, where 0 represents, okay, so we can do for row for r comma c in kernel, right? So we have the individual row and the individual column. Now what do? We do so r comma c is the key. It is the key, right? So this is gonna be something like -1 comma -1. Okay, now we can do for row in range image height, then we can do for call in range image width, right? And then we get the color. So the color is gonna be get pixel or image, and then it's gonna be row minus r column minus c. Okay, and actually this is gonna be so okay, so we get the 3x3 image. We do plus equals, right? to so we can set color equals 0 here, and we can do plus equals I'm just gonna do this color equals color plus get pixel, so right, times my kernel r comma c, right? After all that, what we do is we do set pixel result row comma column comma color, and then we return round and clip of our result. Okay, if this works in one try, I'll be happy. Yeah, it didn't work in one try, but I think we're close. I'll debug this a bit later. Okay, so let's debug. Um, we'll start with correlate small, and if that's a manageable size, then we'll debug that. And if not, then we can write our own test cases and then try to debug, right? But let's see. Yeah, this is definitely a manageable size. Maybe. I don't know. Okay, so we have our test image, which is a 5 by 5. Each of them are 10 pixel. Each of them has the value 10. I'm setting the value at 2 to be 225, 255. So we're doing 0 0. So there's 1 at 0 0. That's it. So at which test case are we failing? Let's see. By test. Yeah, let's do correlate. Yep. Okay, we are apparently passing a few of the test cases for correlate, so that's interesting. So we're doing something correct, and then obviously we're doing something wrong. We're doing most of the things wrong. So we're passing mushroom 0, 2 cat 0, and chess 0. Which, I mean, think the calculation is a mistake. Because by 0, if that means that we're doing multiplied by 0, you know. Let's see. Correlate small. Okay. So we're failing this one. Yeah, we're failing this one. So this is at 2 1, we have negative 1. Let's see how our kernel should actually look. This is just one dictionary. It's not. So I was thinking of, if it has 2 1, then it should also have, you know, negative 1 1, things like that. Interesting. So for the kernel, we're not gonna be given a whole dictionary word. They're only gonna be given the value or there's something occurring. So for -10, we have 1. That's the only thing that we're gonna be given. Right. So that changes that's like a misconception that we had. I think we need to fix our logic. So we don't even know the size, right? Well, if we didn't know the size, then we would have gotten a key error. Because if you know, we are calling with R comma C, and we don't get any key errors. We get assertion error mostly. Well, it's because we're calling with R comma C. I get it. That's why we're not getting the key error. Wait, that is interesting. The reason why this is working is because it says 001. So the only value that we care about is the center value. So the images is gonna be exactly the same. Right. And we fail from here because so let's try to look at this example. So we have 5, 5, 5, 5, 0, 5. Okay, that is expected. Where do we start failing our test cases from? So we failed this one. Surprisingly, we passed this one. Or do we? Let's do this. Let's just focus on the small thing right now. So correlate underscore small, right? Yeah. So you're saying this works? Oh. Oh, I see. The first one works. The second one. First one we're doing the compare underscore images. For the second one we're doing an out. This is the expected value, and then okay. So nonetheless, I mean, I don't think so either one of these are gonna pass. Like if we were to compare images here, um, I don't think so it was gonna pass. Let me just change it up. Yeah, like I said, yeah, I didn't expect it to pass. Okay, so let's look at our original image. That's just gonna be 10, 10, 10, 10, 1, 2, 3. Okay, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, and then 10, 10, 10, 10. Okay, nice. So our correlation is just 1.5 and -1. So we don't know how big it is. All we know is that at 1 1, so this is 0.5, and then if this is -1, this is 0.5. Everything else is 0. So this can be a lot more zeros. We don't care. We only have these two values. Okay. So this is the center value, right? So what are the values that we care about? Realistically speaking, we only care about these values, right? So this is the center value. Whatever value we have, 1 pixel to the right, one pixel to the bottom. So this one, 10. Because if we had this as the center value, let's say this, yeah, we would have only cared about. So this, I'm just considering this is a 3x3. We care about this one, and we care about -1 and -1. But in this case, this is just gonna yield us 0, right? So it should work. I mean, theoretically speaking, right? So we're doing R comma C, right? And then we're doing row minus R and column minus C, okay, times whatever the kernel value that we get. We have that as the color, and then we set it. So we're getting 0, which indicates that we're not really updating anything in color. So let's see, in this example, we are supposed to get, at first it's going to be 1 1, right? So that should give us a 0.5. So 10 times 0.5, that should give us 5, right? And then we have that 5 here, and then it should give us 0. So we have that. Yeah, so let me just, you know what, let me just print color. Now if we run, okay, so there's a lot of things happening, but we get 10. Why would we get 10? It should be 5, but we get 10 for some reason. That is interesting. So we get 10. That is crazy. And our get pixel thing works. I mean, yeah, so our get pixel definitely works. These test cases are pretty well written, so getting 10 shouldn't even happen, because we were doing print color, right? Okay, because we're doing let's see, print or no, okay, what the, oh yes, we're doing, okay, I see. So at first we're doing the 001, and then we're doing 1.5, and then that's where we're getting 10. Print kernel, and then we can do print color. Okay, so okay, 10 is fine. Okay, we are you know what I'm gonna do, R comma C, that is better. Okay, and then I'm gonna go here, and then I'm gonna try to debug it like this. Okay, so we have, okay, so in here we have 1 and -1. So when we do 1 for 0, so it's gonna be 0 plus 1 for the row. Why did I do minus, I wonder? Now imagine if my entire function is correct now. Well, it doesn't even work on correlate small, so there's that. or did we save it? Because sometimes we forget to save it. So we did save it. It still doesn't work exactly. Okay. Okay, so 1 we have 5.0. We also have 5.0. Nice. It looks to be correct to me. It says pixels don't match. Where are we not matching? We're getting what? How are we getting 0? Because it looks to be matching to me. Yeah, I mean, let's see if we print color here. Dun, 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 yeah, we're doing 5.0, 5.0, 5.0, right? So 1, 2, 3, 4, 5, and then 0, and then 5.0, 132.5, 10, 10, 5. Why is this 132.5? What? Well, that's why we're not comparing. We're only comparing with this. I understand that. But that should work. In my opinion, that is correct. But it's not matching what we want it to match. It just isn't. Yeah, I mean, okay. Let's see. Where are we wrong right now? Okay, so And for some reason I'm getting 0 as the color, but I'm changing the color. What is the parameter for set pixel? Yes, so it's the result, the row, the color, the column, and then the color that I want to set, which in this case is this one, right? But when I'm doing that specific thing, I'm not getting what I want to get. Why would that be the case? I'm getting, yeah, so just to like, I'm getting 5, this is correct, 5.0, 5.0, 5.0, 0.0, 5.0, 132.5, 10.0, 10.0, 5.0, 5.0, 10.0. So yeah, this is actually correct. Yeah, I'm getting what I want to get out of the calculation, but for some reason when I'm doing the set pixel thing, it's just not setting the pixel. Strange, right? I mean, what if I do color after the set pixel thing? Print color row column. Yeah, I mean, why not? It's all the information out there. So yeah, so at 0, 0 you want to set 5.0. At 0, 1 you want to set 5.0. At 0, 2 you want to set 5.0. At 0, 3 you want to set 5.0. Strange. Yeah, it's actually printing out what I wanted to print out. So what seems to be the problem? So is it round and clip? Is the problem? What if we do round and clip image result? Okay, so for some reason for the other one it's just doing 0, 0, 0, 0, 0, 0, 0, which I mean I don't understand. Well, let me try to think. Well, yeah, I mean, I expect it to be that, but I suppose that's not what the lab expects. Lab doesn't expect the round and clip, I suppose. So suppose we can do return result, and hopefully that's enough to please everybody. Here, okay, small dubs. Nice. Fast correlate. So much for being hard. Okay. Now let me just do a full test.py just to make sure we didn't break anything. Okay, so blurred is the only thing that we didn't break. Correlate apparently works. Okay. um cool. So now let me bring this back up and let me check my result. Okay, so when you implemented your code and are confident that it is working, try running it on bigbird.png with the following 13 by 13 code, which is all zeros except for a single value. So this one is 1. How would we represent this kernel as a dictionary? Type out the corresponding dictionary below. Interesting. So it's 13 by 13. So so it's gonna be 7 by 7. So 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So this is the center value 7, right? So it's gonna be if this is 0 0, -1, -2, -3, -4, -5, -6, -6, and then -1, -2, -3, -4. So -6 and -4, right? So -6 -4, or actually -4 -6. Yeah. So let me just see if this is correct or not.
George, are you on radio? Yeah. Can you bring me?
Okay, so yeah, it's correct. So it's -4, -6, 1. Okay, cool. So big bird image. So we're gonna have to correlate on that. So it's let's see. We can write our yeah. So yeah, I'm gonna do this, and then let's do this again. X equals to let me just have the code up here. So x equals to load underscore image. So it's test underscore images slash it's gonna be bigbird.png. Okay, so let's look at the image. Okay, cute. So y is gonna be correlate of our image, and then we need to set a kernel. So kernel is gonna be -4, -6 to 1. Set our kernel, and then we can do save image y comma correlate underscore bigbird.png. Okay, let's run the code. Python 3 lambda py. Okay, let's see the image. I mean, I can't tell the difference aside from it being. Actually, no, I can. This side is gone because the leftmost, or yeah, the leftmost column gets replaced. Cool. Okay. Now the next part is what is that gonna be? Okay. So blurring and sharpening. For this part of the lab, we'll implement a box blur, which will make a blurry version of the input image and which can be implemented via correlation. Okay, for a box blur, the kernel is an n by n square of identical values that sum to n. Notice that we have provided an outline for a function called blurred in the lab distribution. Read the docstring and the outline for blurred to get a sense of how it should behave. Okay, let's see. Blurred. Create and return a new grayscale image representing the result of applying a box blur with the given kernel size to the given image. This process should not mutate the input image. Okay. Before implementing it, create two additional test cases by filling in the definition of test blur black image and test blurred centered with the following test. Box blurs of 6x5 image consisting entirely of black pixels with two different kernel sizes. The output is trivially identical to the input. With two different, you should be able to compute the output manually. These test cases can serve as a useful check as we implement the box blur. Once you've implemented your, do not need to okay, fair enough. So we need to do blurring and then sharpening. That's the only thing that is left. Okay, so the main thing for blurring is we'll block box blur. Let's read it. Okay, is a spatial domain linear filter in each pixel in the resulting image has a pixel a value equal to the average value written by the matrix. Okay, so I think I sort of understand. So it can be 2x2, it can be 3x3, it can be 4x4. It doesn't matter. The fact is that all the values have to sum up to 1. Okay, so let's start coding it up. Blur, where is blur? Blur kernels. Okay. Yeah, test blurred black image. Okay. So for this, it's gonna be input equals to, so mode grayscale, right, and then height is it's gonna be 6x5, so height is gonna be 6, width is gonna be 5. Okay, and then pixels is gonna be empty, right? What am I saying? It's not gonna be empty. It's a black image, so it's gonna be 255 times image height, not image, input height times input width. Okay, cool. So that's my input. Now I want my kernel, which is with 2 different kernel sizes. Okay, so we can do let's see, we'll do 1 by 9 and we'll do 1 by 4. That should be good, right? Yeah, we'll do 1 by 9 and we'll do 1 by 4. So kernel, so we can do kernel equals to, is there a smarter way than to just manually type it out? -1 probably there is, but I feel like it's kind of trivial right now. Like I don't think it's fine, you know. Yeah, I think I'm gonna do the smarter way. Kernel equals this. Okay, so for I in range from -1, we want it to go to 2, and for j in range, same, for -1 we want it to go till 2, right? And then kernel dot set, I mean, okay, let's just do that. If I comma, okay, if I comma j not in kernel, it's never gonna be in kernel, it's always gonna be different. So yeah, so kernel I comma j equals 1 by 9. Okay, so that's for the first one. Okay, now we need to do the value by hand. for the 6x5 image. Or bad practice, it's probably pretty good practice, so might as well do it. Safari, okay, so 6x5 image, so it's gonna be 255 250. It's a blurred black image, so it's, what am I doing? It's 0. It's not 255, it's gonna be
Hey,
0.
George.
Okay, so now let's see. Okay, so it's gonna be so 0 0, so 0 0 0 0 0, so that's 5, and then we're gonna keep doing this, right? 4 as the 5th value, and that's the 6th value. Okay, cool. So we have that as our black image, and then we have our kernel, which is 1 by 9 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 and 1 by 9. So our resultant image is gonna be all zeros. That's just, I mean, of course it's gonna be all zeros. So what are we supposed to do with that? It's gonna be all zeros for the other one as well. So okay, so yeah, so we're gonna have an output image out equals to lab dot so output equals to lab dot correlate, and then we're gonna put in our input comma our kernel, right? And then at the top we're gonna do an expected equals to mode grayscale height 6 width 5, and then pixels would be 0.0 times times 6 times 5, basically 6 times 5. Okay, 6 times 5. Okay, cool. Okay, so we have our output. Now we can do compare images out comma expected, and then we can also do exact equals to false, which should be exactly the same, but you know. Let's do another kernel now for I in range. So let's do this kernel. Okay, so for I in range -1 to 1, for j in range -1 to 1, kernel I comma j equals 1 by 4. Okay, and then out equals to lab dot correlate input comma kernel. Okay, kernel, and then compare images, right? Compare images out comma expected exact equals false, and then the hashing thing, right? Input hash. Okay, where is that? Where is blur? Okay, yeah, so input underscore hash equals to object underscore hash input, right? And then in here assert input equals to input underscore hash, otherwise, yeah, be careful not to modify the original image. Be careful not to modify the original image. Okay, cool. So that's this thing done. Now it says blurred center pixel. So that's gonna be all 255s. So it's from 1 to 55, right? Which is the center pixel. So for that, let's see the input. I'm just gonna do a 3x3 image. Mode grayscale, and then height 3, width 3 pixels is gonna be, so it's gonna be all 255. So 255 255, that's 255. So 1 2 3 4. So 1 1 is basically gonna be yeah, so 1 1 is basically gonna be 0, correct? So that's gonna be the fourth one. So 0 1 2 3, yeah, this is gonna be 0. So it's 0 1 2 3, the fourth one, and then 255 255 255 255. That's it, right? We have 1 2 3 4 5 6 7 8 9. Yep. Okay, now let's do the input hash equals to object underscore hash input. Okay, now we can do kernel, and our kernel, it's gonna be the same thing, right? -1 to 2, j in range -1 to 2, right? Or kernel I comma j, that is gonna be equal to 1 by 9. Okay, and then the output is gonna be lab.correlate. Oh, not correlate, blur. Yes, blurred. Yikes, this is just gonna be a kernel size. Why am I making a different kernel here? Okay. Yep, so yeah. So kernel size is gonna be what is kernel? Is it gonna be 3 or is it gonna be like 9 and I'm supposed to know it's 3 by 3, right? There's a better way to do this. Current size is 1, 3, and 7. Yeah, there's no way there's a kernel size of 3. That's impossible. Okay, so I see. So this is gonna be 3, and then this is gonna be 2. Yes, so same here. This is gonna be 2. Lab.correlate, not correlate, blurred, right? Out gamma expected, but there is no expected. So yeah, let's actually calculate the expected now. Okay, so we have 255, 255, 255, 0, 255, 255, 0, oh no, 0, 255, and then 255, and then for our kernel we have 1 by 9, 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 1 by 9. Okay. So it's gonna be the same value throughout except for the middle one, right? Or not, it's gonna be the same value, period. 255 times, what is 1/9? I'm just gonna do the calculation here. Calculator. Okay, 255 times 1/9. So whatever value we get, 1, 2, 3, so times 8, right? Times 8, so 226.7. And that's gonna be the value that I'm gonna put out for all the thing. That's how it's gonna be blurred. So expected is basically gonna be the same thing, except expected. Okay, close Safari. Yeah, expected, aside from the fact that it's gonna be 226.67 times 9, right? It's gonna be this value, but it's gonna occur 9 times. Out comma expected exact equals to false. Oh no, lab.blurred out comma kernel, right? And then compare images, out comma expected exact equals false. Okay, and this was kernel at 3. Now we can do kernel of size 2. Okay, so it's the calculation for a kernel of size 2. It's gonna be slightly different, I'm pretty sure. Okay, that's gonna be 1 by 4, 1 by 4, 1 by 4, and 1 by 4. So for the first one, it's gonna be these 4 values, right? So 255 times 1 by 4, 650.75 times 3 times 3, 191 point 191.25. For this one, it's also going to be the same, 191.25. Or did I make a mistake in the calculation? Maybe I made a mistake. Also for the whole 3 by 3 thing as well. Let's see. Okay, we have 255, right? So this would be the center value, right? This 255. Okay. Okay, so we won't have any of even number, so it's never gonna be 1 by 4. Okay. So I'm just gonna do 1 and 1 by 3 because these two are the smallest. So let's say if it's just 1. So 1. Then we're gonna get the exact same thing back. So this is what I'm gonna do for the first one. Kernel size equals 1. Okay. And then that's fine. We're gonna get the exact same thing. So this part is golden, and then we can do the same for here as well. 1. The expected is gonna be exactly the same as this. Yeah, right. Depending on if it's either 1.0 or 1, we might get float, we might not. But yes, I'm gonna do 255.0, right? Okay, so this is exactly the same, right? Okay, so this is when the kernel size is 1. Now let's do kernel size of 1 by 1 over 9, that is 3, right? So 1 over 9, 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 1 over 9. And then I know for a fact that this is going to be 0 no matter what, because we're not doing any calculations here. So the black image is fine. Okay, so we have 255. That is going to be the center value, right? So this is negative 1 1, so this is going to be 0. Okay, so this is gonna be 0, and then this is also gonna be 0. So above all of this, this is gonna be 0. This is gonna be 0. This is gonna be 255, and then this is gonna be 255. No, because this is gonna be 0, 255, and then 0. So we're doing 1 here, 1 here, 1 here. That's 4, but the rest of it is gonna be 0. Okay, cool. So it's 255 times 3. I mean, this is the correct, it's 191.25. But is it the same for all of it? That is the question. Because it shouldn't be. Because now if we look at this one, this is gonna be 255, and then actually 255 here. Sure, it's gonna be all 0 here, but it's gonna be 255 here, 0 here, and then 255 here, right? So for this one, it's actually more than 1 by 9. It's gonna be 3 plus 2, so 5. So 63.75 times 5. That's gonna be 318.75. 318.75. So I'm just gonna write that down. The first one is 191.25, 191.25. Second one is 318.75, 318.75. Okay, the next one is gonna be this one, which is gonna be 255, 0, 255, right? All of the above is gonna be 255. The one below it is gonna be 255. It's gonna be 0, and then this is gonna be 0. So that is gonna be 191.25. 191.25. Okay, so we add that 191.25. Okay, and now this one is the center, so 255, right? The one above that is gonna be, so this is gonna be 0, this is gonna be 0. gonna be 0, 255, right? 255, 255, no, 0, 255, 255, 1, 2, 3, 4, 5. So 318.75. Just because of that one dot, it's okay. This 0, for this 0 it's just gonna be this is gonna be the maximum number possible. So 1, 2, 3, 4, 5, 6, 7, 8. 63.75 times 8, 510. Actually, y equals to round and clip image. Y, yeah, we should have done that. Let me just run, and now we can see correlate better. You're gonna round and clip after that. So yeah, where were we? So yeah, this is gonna be 510. Okay, and then now if this is the center, 0, 0, the one above this is 255, 0, 255, one below this is 255, 0, 255, 1, 2, 3, 4, 5. Okay, so 5 is again 318.75, right? Okay, and then this one, right? So this is 0, 255, the one above it is 255, the one besides it is 0, this is 0, the one below it, all of them are going to be 0. That is going to be 191.25. Now this and this should be equal. Now, did I make any mistakes in calculation or not? We can find out right now. Okay, so 255, the 2 besides this is going to be 255, 255, and above it is going to be 0, 255, 255, 255, 255, and 0, 0, 0. So 5, that's going to be 318.75. And the last one should also be 191.25. Right, okay, so now we can do out equals to lab dot blurred. Why are we doing out here? Input, and then in here as well, input comma kernel. Okay, compare. Let me just show the code now since we're done calculating. Compare images out comma expected exact equals to false. We have compare images, and then now we can do cert input equals input hash, right? Be careful not to modify the original image. I think I know what's happening in input hash. So we're passing it through all these compare images in blurred function, and then we're seeing if the hash function returns the same. If it's the same then it's correct. If not, then we say be careful not to modify the original image. Okay, I think we're ready to code it up, right? Yeah. Yeah, I think we should be able to code the blurred thing up. Okay. After blurred, we have sharpen, and that's it. Okay. So we need to generate a kernel. That's it. For the given kernel size. So if it's 1, it's just gonna be 1. If it's 3, then what are we doing? We're gonna go from this is generating a kernel. That's the biggest part of this thing. That's gonna be a dictionary, right? We're gonna have to generate that dictionary. So if it was 3, we're doing -1 to 2. For 7, we were gonna do from like, it's gonna be of a range 7. Let's see, I can't calculate it. Let's try to do a 7x7 kernel. Let me just try to draw one. Maybe that'll help me. 1, 2, 3, 4. Let me just share Safari as well. Okay, so if we have 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. 2, 3. 1, 2, 3, 4, 5, 6, 7. This is 5 by 5, right? So what is the center one? Okay, this is not 5 by 5. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay. So 3 by 3 maybe. Nope, it's gonna be 4 by 4. It's this one. One, 2, 3, 4, 5, 6, 7, 8. Yep. Nope. There we go. So it's this one, the one at 4. And yeah, it's this part. This is the middle. So it's 3 by 3 is the middle. Or a 7 by 7 kernel size. What can I do with that information? So if we do kernel size, if we divide that by 2, or a floor division, if we do that, so we get 3 here. We are iterating from so it's gonna be minus this is -1, -2, -3, 1, 2, 3, right? And for 3 by 3, what are we doing? So we're gonna get 1, right? Yeah, so if we iterate from the negative of the division all the way to the positive plus 1, because we go up to but not including that, that is the dictionary, right? So yeah, so I think I have the algorithm. So k equals to kernel underscore size floor division, right? Okay, so we did the floor division. Now for I in range minus k to k plus 1 for j in range negative k to k plus 1. Let's do kernel. Okay, and then kernel I j, this is gonna be j. Okay, kernel ij equals now the final thing is it's gonna be 1 by, so if it's a kernel size of 3, it's 3 squared. 7, it's gonna be 7 squared. So 1 by kernel sized whole squared. Okay. Now we return the correlates. We did the hard work of image comma kernel. This should work. Okay, so I'm gonna do the test. It never works in the first try, but you know, by test, I'm gonna do test.py the whole thing. Okay, blurred. I think this is because modes must match, huh? Okay, this is probably as my test cases. I didn't write it properly. So let's see. Blurred back black image. Okay, so it says cannot access. Okay, now let's just test blurred because the rest of it passes. So it's just blurred. By test, yeah. So blurred. Okay, it does pass a few of them. Okay, so cannot access local. Honestly, let me just do blurred underscore black underscore image. Okay, yeah, that's my bad. I should just hard code does 6 times 5, no? Interesting. So it should be, my bad, it should be grayscale. Grayscale, right? Because when we're doing correlate, what was it called? Or inverted to, yeah, it's called grayscale. It's a typo, silly typo, but grayscale, and then grayscale, save it. Okay, now let's try to run it. Okay, be careful not to modify the original image. That is Very fair, I suppose. Should not mutate the input image. We are technically mutating the input image, aren't we? Okay. Because even when we call correlate, I mean, are we though? Because we're calling correlate, and correlate should return a result, right? I should just get the pixels from. How to copy dictionary in Python? How to copy dictionary in Python? I was gonna do import copy.com. I was gonna do copy.deep copy, but I can't do that because I cannot import any modules, and deep copy isn't why is it changing the mutation shit? Because does that technically make sense? I suppose, because we're doing input, we're passing in kernel, right? And what is it doing? It's passing the input, the image, and the kernel size. But when it's passing the input, it's passing it to correlate. And what is correlate? Correlate is doing a result thing, so it's creating result, and then it's returning me the result. I suppose we can do something like this. Result equals what is it? Mode, right? Right. So we have result, and then for pixels we'll do this, and then for pix in image pixels, right? Result pixels, but append pix, yeah, and then here we pass in result. How are we modifying the actual image right now? No, we can't, because that doesn't make any sense. We're not even doing anything with the actual image. That means something wrong with whatever I typed in, not. Doesn't make any sense for me. Where are we failing again? The blurred black image, right? Let's see. how are we modifying the image? I have no idea. What? um I see. Yeah. Okay, so we need to do so we need to do check underscore hash. So right now we're gonna hash the input, right? Copy this, and I think I don't need to do this. That's all I'm saying. I did this because I was like, maybe there's something wrong, but we should be able to just pass in image and this should work. Okay, the for a black image thing passes. Okay, centered pixel doesn't pass. Center. Okay, center pixel. Okay. Pixel value expected 191.25. 9 pixels had incorrect values. Interesting. Very interesting. You know what? I should actually make sure that my test case is actually okay before relying on my test case too much. So let me check. Apparently I made a calculation error. Okay, so oh my god. Okay, so the calculation error is this part. So it's gonna be 255.9. That's 28.33. So why did I get something else? Bro. Oh my god, I did 63.75. That's the one for. So let me see if I remember it. This was 5. This was 3. This was 5, right? This was 8, correct? So let me just verify it. So I'm just gonna cross check it. That's what I was thinking, like maybe I miscalculated it. It shouldn't be 510, right? Okay, so 255, if we consider the first one value is a center value, so anything to its right is gonna be 255, to its left is gonna be 0, to its above it is gonna be all 0. This is gonna be 255, 0, and then 0. So this is 3. So we have 28.33 times 3, that's 85. So 85, and then this is for 5 if I'm not wrong. Yeah, there's 5 and there's 8, so 28.33. so 28.33 times 5, that's 141.667, and then 85 again. 85 again, this is for 8. Oh, this is for 5 again. What am I doing? Okay, so this is 85. So I'm gonna do all the 85s at first. 85. Any other 191? 85. And then this is also gonna be 85. And then I'm just gonna 0.0, 0.0, 0.0, and then 0.0 here. Okay, and then for the 318.75, it's gonna be 141.667. So yep, and then 2 more. 141.667, and then this is also gonna be 141.667. Cool. And then the last one, so 28.33 times 8, that's 226.667, right? So copy that, paste it here, save it. Now let's run my test cases. Okay, centered pixel passes. Now let's run for the rest of them. Okay, so a lot of them still fail. These are other test cases that are failing. So 5 passed, 6 failed. Okay, mushroom 3. Ay. Mushroom 3 and mushroom 7. Okay, so where is mushroom? Okay, Huh. Perhaps return round and clip img. Okay, now this is cool. So 0, and then this is pretty easy. 255, 255, 255, 255, 255, 255, 255, 55. How does the Python round function work? So above 5.5, I think it rounds up, right? Yep. So okay, so where is it? Blurred. Okay, 255, and then this is gonna be 85. This is gonna be 142. Right, 85, 142, 227, 142, 85, 142, and then 85 again. Cool. There we go. Everything passed. Okay, now what are we supposed to do? Okay, we're gonna do that on cat.png, and then we're gonna save the result as a png image. And the kernel size is gonna be 13. Okay, cool, let's do that. Clear. Okay, comment these out. Okay, let me look at cat.png. Okay, so this is gonna be a blurred black and white picture of this. So x equals load image test images cat.png, right? png. Yeah, and then y equals to blurred x, and then we can do blurred x comma 13 is the kernel size, and then we can do save image y comma blurred for cat.png. Okay, cool. Let's run this Python 3. Okay. Oh yeah, this is very much blurred. Okay, cool. Now what do we have? We have one more function to write. I think that's called sharpening. Next, we'll implement the opposite operation known as sharpen filter. The sharpen operations often goes by another name which is more suggestive of what it means. It is often called an unsharp mask because it results from subtracting an unsharp blurred version of the image from a scaled version of the original image. More specifically, if we have an image I and a blurred version of the same image, the version of the sharpened image at a particular location is one way we could implement this operation is by computing a blurred version of the image, and then for each pixel compute the resulting value given by the equation above. Okay, I think we have all the puzzle. While you're not required to do so, it is actually possible to perform this operation with a single correlation with an appropriately chosen kernel. Okay, so I'm not required to do so, but if you want to use the blurred version that was made with a 3x3 blur kernel, use to compute S in its in single correlation, I without producing blur at all. So let me think. So we do 1 by 9, right? But image is an image, and kernel set denotes the size of the blur kernel that should be used to generate the blurred copy of the image. You are welcome to implement this as a single correlation or using an explicit subtraction. Though if you use explicit subtraction, make sure you do not do any rounding until the end. Not blurred or clipped in any way. So is it possible if I do so it's 2 times that, right? Minus the blurred. Yeah, I'm just gonna ask AI for this because this, since it's a strictly, you know, yeah, I think I'm just gonna do the easier method since I'm not required to do so for now. Yes, we have our image. We need our result, which is, yep, it's gonna be this. We need this line of code for sure, and then we also need these 2 lines. Yep, and then what do? So we need to do a blurred, we need to have a blurred image. So blur equals to blurred. We pass in our image and our kernel size. We have our blurred image. Okay, now we can so we can just directly go inside result dot set what was it called? No, set pixel. Okay, set underscore pixel, not dot. You can just directly do set underscore pixel result row comma col, and then for the color, let's see, we'll do it's gonna be get underscore pixel for image, so it's gonna be 2 times get underscore pixel for image comma row column, right? And then subtract that from get underscore pixel from blurred comma row comma column, right? And then we set that as the color. Okay, and then we return round and clip image of our result, and that should pass all the test cases for blur, and technically it should pass all the test cases, period. So let's do pytest test.py. Oops. Oh, sharpened. The function object is not subscriptable. Huh? Where am I doing that? let's just do this. The sharpen, let's just do, where is sharpened? Okay, let's just do sharpen like all of them, honestly. Yeah, okay. Pixel, blurred, row, comma, column. Huh? What does blur return me? Blur should return me an image, right? Oh, I did blurred. It should be blur. That's what I'm saying. Okay. Nice, it passes, and I'm just gonna do a full test case. Brilliant. Okay, so that's the first lab done. It was lengthy, but it wasn't that bad. It wasn't that complicated. That's all I can say. It was just simple arithmetic operations, right? Well, technically I'm still gonna do the sharpening thing, so I'm gonna try to sharpen the image. So python.png, where is that? Okay, let's see if we can sharpen this. Okay, so sharpened, right? Kernel size, what should be the kernel size? 11. Okay, 11, and then save image, comma, sharpened for python.png. Okay, let's run the code. So this is definitely sharper, but it's PNW. Yeah, so when I do the RGB images, it's probably gonna be even more